So to begin, I'm just going to talk about what is compositing and what we're talking about in this context of using compositing in safety critical applications. And so compositing is the ability to overlay video content on top of other content, or video or still image content on top of other video content. And it can be used for reusable components. And reusable components is the part we're really going to focus on this presentation. But I'll give an example below of a scene that has been composited on the news. So if you look at the scene, you can see that there's the main video, so the newscaster's talking in the background, and then on the top, there's a marquee at the bottom with the breaking news and then news at the bottom. So this marquee that's displaying text at the bottom would be a composited content on top of the main video. So as we can see from this example, compositing is used extensively in commercial video and commercial solutions. And so here in this presentation, I'm going to be talking about how we can use it in safety critical applications for reusable content. So to give an example of compositing components and reusing them, I'm going to break up the compositing process and just give a real concrete example of what we're trying to talk about here. So in a compositing situation, you would have several off-screen applications that represent your components, and you would have a compositor application that is responsible for taking those off-screen components and arranging them on the display to make the final image. So in this case, we're going to have the first application run, and it will draw a speedometer. So this example I'm providing here is going to provide a composite an entire car's dashboard. The second application that's rendering to an off-screen buffer is going to draw a tachometer. And the final application is going to draw a GPS navigation system. So we have all three applications responsible for an individual component. So the only thing they have to worry about drawing is this individual component. And then the compositor application will come along and it will take the GPS navigation map and place it on the final screen. It'll take the speedometer and composite it on top of that. And lastly, it will take the tachometer and it'll composite that as well. And you'll be left with the final composited vehicle dashboard on the right. And so when we're talking about compositing components, this is what we're really focusing on, breaking the graphical elements of your project into individual applications that are responsible for rendering individual components, and then taking those components and combining them in a bigger application. To go more into where compositing is supported, so two of the major graphics APIs used in the safety critical space, so OpenGL, specifically OpenGL SC, and Vulkan, and likewise with Vulkan SC. There's two extensions to the graphics library, one for each API, that adds support for compositing. So for the OpenGL spec, there's an extension called the EGL ESD compositor that provides this compositing functionality that we're talking about, and I'll go into more details about the that extension. And likewise for Vulkan, there's the VK-KHR display extension, which also provides support for compositing, as well as a number of other display features for Vulkan. So I'll go into more detail about OpenGL and compositing, as well as Vulkan and compositing in the following slides. So what is Vulkan? First off, because not everyone is as familiar with Vulkan, as it's a brand new API from the Kronos group. So Kronos is the group that does the OpenGL graphics standards. So they develop graphics and basically GPU focused standards, mainly around graphics and compute. And so their next generation of graphics API is called Vulkan. It's an open standard like OpenGL, publicly available, but the main difference between Vulkan and OpenGL is that Vulkan is much more low level, and it allows the application to have full control over the GPU, exposing both the graphics side of the GPU and the GPU compute side, allowing you to do both graphics and then parallelize compute as well. And as mentioned, it's much lower level. So compositing in Vulkan makes use of the VK-KHR display extension. The way this works is that an application, so in a compositing context, there's an off-screen application and there's the compositor application. The off-screen application will render its content into an off-screen frame buffer object. And that frame buffer object will have a display ID associated with it. And then the compositor application can come along and take that display ID and use it to access the frame buffer texture for that other application, allowing the compositor application to bind that frame buffer as a texture and then use it as you would use any other texture from within Vulkan. So this is an open extension, publicly available. There's nothing proprietary about it. It's part of the official Vulkan extension list. And one of the, I guess, key important things here, especially for the context of compositing and safety critical, is that off-screen surfaces, so the off-screen application surfaces, can be shared across processes, partitions, and guest operating systems. So if you're really focusing on isolating lower DAL level components of your display, they can be running in a separate partition or in a separate guest operating system that's certified to a lower level, and a compositor that's certified to a higher level can still access that content that's isolated in a different partition through a safe mechanism. So that basically covers what compositing is from the Vulkan side. Now let's look at the OpenGL side. So OpenGL is an older graphic standard from Kronos. It's existed for a while. It has its safety critical equivalent, OpenGL ESD. Like Vulkan, it's also an open standard, publicly available. The big difference between OpenGL and Vulkan, like mentioned before, is OpenGL is higher level than Vulkan. It doesn't give you as nitty-gritty access to all of the functionalities in the GPU. It doesn't expose, at least the older OpenGL standards and the safety critical standards don't expose the programmable nature, the full programmable nature of the GPU. So they do provide mechanisms for doing shaders for vertex and fragment shaders, but they don't expose compute shaders, for example, or geometry shaders or tessellation shaders. The other big thing about OpenGL that makes it easier than Vulkan is it handles a lot of graphics related state for an application. So it removes some of the overhead you might have with Vulkan, whereas with Vulkan, it allows you to set it up so the application can take the most optimal route for storing state. So compositing in OpenGL. This makes use of the EGL ESD compositor extension. So those of you familiar with OpenGL would know that there's a distinction between OpenGL and the windowing library on top of it. So a standard library that's provided with most embedded OpenGL implementations is the EGL library. And this EGL library has an extension called the EGL ESD compositor extension that allows composited surfaces to be used within EGL and then passed to OpenGL. So the way this works in OpenGL is that a compositor application allocates several surfaces for an off-screen application to use. And the way the off-screen application accesses those surfaces is that each surface has an ID associated with it, and they will request that surface with that ID at initialization, and the driver will give it that surface. This surface can, like Vulkan, be shared across processes, partitions, and guest operating systems. So you get again, the key benefit where a application that's rendering a component in either in a different partition or a different guest operating system can share the content that it's rendering with a compositor that exists in another partition or another guest operating system. Another big benefit of the EGL ESD compositor extension is that it's FACE aligned. So those of you familiar with the FACE consortium, the EGL ESD compositor extension was developed in the FACE consortium to fill a need for compositing solutions for reusable aircraft systems. So it's FACE aligned and it's really designed around making stuff more reusable. So to just hopefully get it more into your mind about the kind of architecture we're talking about for applications, In the compositing system, each graphics application that is rendering off-screen has an off-screen buffer associated with it. And that off-screen buffer is shared between the compositor or window manager application and the graphics application. No other application on the system can access that off-screen buffer. So you can see through these arrows that the graphics application can draw to the off-screen buffer, and the compositor application is able to read and only read from the off-screen buffer. So this all prevents, the compositor from corrupting the state of the graphics display or other graphics applications on the system from corrupting the frame buffer of other graphics applications on the system. So hopefully that gets the picture in your mind about compositing architecture and what exactly it looks like and what we're talking about here. So both the EGL ESD compositor and the VK-KHR display extension allow for windows with transparent backgrounds. So this is a very important component for representing widgets in an application. And to illustrate that, I have a picture of a primary flight display below. And if you look on the right side, you can see several widgets or components that are on top of a black background. So for a component in this case, if you didn't support transparency, it would not be a big deal. Since the background is a fixed black color, you just know to render all of your components with a fixed black color and it would be okay. But if you look more towards the middle where the compass is, you'll see that the compass is actually transparent and that content below the compass is supposed to render through it. If the compositor extensions did not support transparency, there would be not an easy way to represent this content and not a controllable way. Either you would have to take up a binary approach where the whole component is transparent or none of it is. But here you can see that the black part underneath the compass is transparent so that you can see through it, but the text on the compass is not transparent, neither are any of the lines drawn on it. So the ability to use transparent backgrounds on your components is important for representing widgets in a system, and both the display extensions allow for that functionality. The next I'm going to talk about safety critical compositing. And so safety critical compositing has a few requirements, and I've listed those on the right. So one of the big things is we need to ensure that critical elements are always visible. They're not being obstructed. They're not, no other content is being displayed on top of them that would cause them to display hazardous or misleading information. The next important thing is for safety critical compositing, you need a platform with certification evidence. Even if your compositing architecture is safe and certifiable, if the underlying driver and control software is not certifiable, you wouldn't be able to do safety critical compositing. And then the last important component, especially with the emergence of multi-core systems, is support for mixing of high criticality and low criticality components. So on a single large area display, you'd want to display all components for your system. That's, the whole reason that you'd use the large area display, so that you could replace individual displays with one or multiple individual displays with one single larger display. And so if you can't display both your low criticality components and your high criticality components on it, it wouldn't be very useful to have a large area display. So the approach for mixed criticality, the EGL ESD compositor. So as I mentioned before, it was developed with the FACE consortium, and it was actually designed with mixed criticality systems in mind. So the EGL ESD compositor extension gives control to the compositor application to throttle other applications underneath it. So it has the ability to control when the off-screen applications are able to flip their display for double buffer displays. And so this allows the compositor application, which usually is certified to the highest level of the content it's displaying, to throttle the applications underneath it. So another key thing I just said right there was that In a multi-DAL situation, the compositor needs to be certified to the highest design assurance level of the content it would be displaying. So if you have a large area display where you want to show both DAL A and DAL C content, the compositor would need to be certified to DAL A so that it can show the DAL A content safely without interfering with it. And then it can also control the DAL C application to some extent to throttle how quickly it's rendering by controlling when it's actually able to swap buffers for its double buffer display. The other thing about the compositor is that it is in full control of where content is displayed on the screen and how they can overlap. So if there's DAL C content that could potentially cover up or make DAL A content display hazardous or misleading information, the compositor would be able to override that and prevent the DAL C application from rendering on top. Since it's in full control and it'd be certified to DAL A, you'd ensure that you have a safe system in that case. And so with this combined functionality, system designers are able to ensure that lower DAL applications do not interfere with higher DAL applications, and allowing the display to be shared between multiple design level applications. So another part about safety critical systems is that certification evidence, you'd want to reuse certification evidence as much as possible between components. So components, one of the key benefits of the EGL compositor extension is that it makes no assumptions about the underlying display system. So the compositor extensions set up a common framework for an application to request an area or like a frame buffer to render to. And if an application is built using this interface, any new driver that also provides the compositing interface would be able to reuse the same application with no changes. So if there's no application level changes, and if the binary doesn't need to be recompiled for a new system, the same pre-certified binary could be used as is on a new system, and any of the certification evidence carried at the component level could be carried over with that reuse. Now, there would be some system level certification requirements that would need to be retested, but any of the component level evidence or artifacts would be able to be shared across, since there'd be no changes to the underlying software of that individual component. So the key benefits right here with reusing components are, one, you're reducing application development effort. So any software developer or project manager on this call will know that developing software takes a long time. It's a lot of effort. And if you can reuse effort that you already did, you want to do that, especially if you know it's functional, it meets all the requirements for the project you're working towards. And so when you're taking advantage of the EGL compositor extension or the Vulkan compositor extension, it provides this common interface that allows software to be reused at a per component level. And usually you wouldn't want to modify your components too much on a life cycle level. There might be some components you want to revamp and others you want to pick and choose and use as is. So using this compositor architecture, you get the flexibility to take stuff as is and then redevelop individual components that you need to redevelop. Like mentioned before, you're also reducing the certification effort for any of the components you've already developed, since a lot of the artifacts for that component can be reused in a new system. And lastly, something people might not think about is that when you reuse components, you're providing a consistent user experience when moving from a legacy system to a new system. So the operator of whatever device you're developing will be familiar with the old components that you've developed, since they've been using them for however long that project has been in the wild. And so if you're reusing legacy components, the operator will be familiar with those legacy components and they won't need as much training to get familiar with the new system. So just illustrated example here of reusing components. If you have a legacy application, so in this example, this is a cartoon version of a PFD. You can extract a legacy component here. So the horizon indicator is being extracted right here. Taking the horizon indicator and modifying it slightly so that it is rounded and slightly transparent, and then being displayed over a map. So in this whole process here, we've taken a legacy component, or we have a legacy application. We've extracted the legacy component we want to reuse, and then we've modified how it's displayed in some way and composited it on top of a new application. So this would be the whole life cycle of reusing a component, at least visually. So to continue on about compositing, what products can you find this support in? So from us at CoreAVI, we provide the VK-KHR display extension and our Vulkan driver. So our Vulkan driver is called VK Core SE. It has support currently for the E9171 and I.MX8 Quad Max, and support for the VK-KHR display extension. Our OpenGL libraries for that run on top of Vulkan. So this is our VK Core GL SC product, which provides support for OpenGL SC1 and OpenGL SC2. Has support for the EGL ESD compositor extension. Just a note about this library, it is just a library that runs on top of an existing Vulkan driver. But for more legacy GPUs that we support, we have a dedicated OpenGL SC1 and SC2 driver. So this would be our Argus Core SE product. So we have a support for a number of older GPUs on this product line. So for example, the E4690, 8860, the I.MX6, S32V, and there's a few Intel variants we support as well. There's support for the EGL ESD compositor extension on that product line as well. So that covers what I wanted to talk about today for compositing and reusing software. Thank you very much for attending. And if you have any questions, you can ask now.
Hey Lucas, you talked about I think you said the EGL compositor was somehow created through the FACE consortium, right?
Yes, it was. Yep.
Does that ever circle back as part of Kronos then, or is it just that Kronos provides an extension and FACE created this extension independent of Kronos?
So the extension was, so there was a requirement in FACE for some kind of compositing functionality for OpenGL. So members of the FACE consortium developed an extension and proposed it to Kronos, and then it went through the normal Kronos process.
Oh, okay, thanks. I was curious.
Okay, thank you for your question.
I have one more question, if I can ask, regarding the compositing of legacy software and, for example, the one which is written with the new Vulkan SC. Is it possible? Because on the last slide before this one, you were saying that it has different layers for display. And is it somehow possible to mix the legacy software and with the new one or not?
When you were talking about legacy software, do you mean
I mean
legacy OpenGL software?
OpenGL SC1 and 2.0, yeah.
So you could mix OpenGL SC1 and SC2 software since they use the same EGL compositor. Mm-hmm. So if you had a system that supported both SC1 and SC2, so I would just say as a note, our Argus Core product line, there is not support for running both an SC1 and SC2 driver on the same system, but with our VK Core GL product line, you could have that capability where you're running SC1 in one application and you're running SC2 in another application, and they would both be using the same underlying EGL implementation that would allow you to share content across them using the compositor extension.
Okay. So, but it's if let's say I want to composite these two applications with another application which is written in Vulkan, it's not possible now, if I understand properly.
Yeah, that's correct. So that's currently not possible. So another extension would need to be developed to create a common language between the VK KHR display extension and the EGL compositor extension, such that their content could be shared across. So that currently does not exist, but it is something we're looking into.
Yeah. Okay. Thank you very much.
No problem. Thank you very much for your question.
I've got one question as well, Jean-François Pouilly from ISIT. The 3 products you presented just before, it's completely fully standalone products. You don't need, for example, VK Core SC to run VK Core GL?
So the Argus Core is a standalone product, and the VK Core SC is a standalone product. The VK Core GL. Sorry. Okay, so the VK Core GL driver or library is just a library that needs an underlying Vulkan driver implementation. So in order to use the VK Core GL library, you would need the VK Core SC driver to run on top of.
Okay, so 2 layers, in fact. 2 layers.
Yeah,
okay.
There's 2 layers for the OpenGL support on the newer GPUs we support, so that 9171 i.MX8. If you want OpenGL support, you need the underlying Vulkan driver.
Clear. Thank you very much.
No problem. Thank you very much for your question.
Any other questions for Lucas? Okay. Well, if you have any questions, if you think of anything later, you can always email Lucas or email myself. Anyway, we thank you all for coming. Hope you enjoyed it and have a great day.
Thank you. Have a good day.
Thank you.
Thank you very much.
Bye, everybody.
Thank you very much.
Thank you.
Thank you.